do you guys see that in a circle?
Okay. I think.
So what about means what can you say about the estimated measure of P or pi? Can you give some more?
Actually, yes, that's been covered by the behaviors. The irrationality method.
Like in complex numbers.
Yes, this is all about order, right? And there's no order on complex numbers. You can't say one complex number is less than the root of another. Today, without, well, not without zero calculus, but without much calculus, I'll show you just how much you can do in the realm of number theory. So let's start with what we call Diophantine. Is it readable? Can you read this? So Diophantine, from Diophantus, who's also famous for the Diophantine equation, the practice of approximating an irrational number with the closest rational number. For example, you are probably familiar with 22/7 being used as an approximation for pi. So, yeah. So this is about the closest that what we're going to talk about today comes to a real physical world application. Very close approximations for irrational numbers that use very small denominators, and so they're pretty convenient to use in real life. So where do these actually come from? Where are they derived from? 22/7 is fairly easy to find because it has a small denominator, but you might have heard of 355/113, which approximates the first 7 digits of pi very accurately with just 3 digits in the denominator. So how does it do that? How do people find this? Especially in the world of 500 AD, when this was first discovered. Well, let's start simple. How do we actually approximate an irrational number? The most famous method, of course, 3.1415926535897. So that's all of them I know. So the most famous method is just truncation, which is what happens when you take some number of the digits and just cut the rest off. But as we'll see in just a minute, this is actually a very bad approximation method in terms of accuracy. Why is this? Well, here's what I'm going to do. Oh wait, the eraser's over here. I am going to define a sequence of approximations. So I'm going to start with approximation number 1, which is going to be the worst. It's what happens when you only take the first digit of pi. Then I'm going to define approximation 2, what happens when you take the first 2 digits. And then I can define approximation 3, which is what happens when you take the first 3 digits. And so on and so forth. 141, 3141/1000. So as you'll see, the general pattern here is that the denominator, so if we write an, because a is a rational approximation, if we write that it's the ratio of these two, the denominator is always going to take the form 10 to the, well, I wrote it as n minus 1. So now, let's write something called the discrepancy, d1. That's just going to be the absolute value of pi minus a1. So it's just going to be the distance between the two. And it's 0.14159, etc. So it's 1.4 times 10 to the minus 1. Then d2 is pi minus a2, and it's going to be 4.2 times 10 to the minus 2. And then d3 is going to be pi minus a3, and it's going to be 1.6 times 10 to the minus 3, since it's going to be 0.001592, and so on and so forth. So you can probably see how the pattern is shaping up here. Qn is going to be on the order of 10 to the n minus 1, and the discrepancy, so the error in the approximation, is going to be on the order of 10 to the minus n. So what it's looking like is that the discrepancy will be on the order of 1 over 10 qn on the order of, which means, it's between 1 over 10 qn and 1 over qn. But what if I told you this is actually, although it seems good, this approximation accuracy is actually really, really bad. You can do much better with the same exact denominators. We have 314 over 100 here, which is only 2 digits of accuracy, when you can get 355 over 113 for 7. So what's the difference between these two? Well, enter what we call continued fractions. What I'm going to do first is a small demonstration. So I'm going to write over 1, over 2, over 3, 4, and so on. And now, I want the integer on the numerator that provides the closest approximation to pi. So this is very obvious. 3 over 1, 6 over 2, 9 over 3, 13 over 4, 16 over 5, 19 over 6, 22 over 7, 25 over 8, 28 over 9, and 31 over 10. Let's remove all of the approximations to the exact same as 3 over 1, so they can't be included. 13 over 4 is fine. 16 over 5 is even better. 19 over 6 is even better than 16 over 5. 22 over 7 is better than 19 over 6. But suddenly 25 over 8 goes too far. 22 over 7 is 3.1428. But 25 over 8 is only 3.125, much farther. And so we have to erase that, and 28 over 9 gets even farther, and 31 over 10 is even farther than that. So it looks like after 22 over 7, there's just nothing. It's a barren wasteland. But of course, that's only because our sample size is 10, right? You can't go off a population of 10, especially when the highest value found is 7, and say, well, there's nothing after 7, right? So what do you predict the next improvement will be? What will be the denominator of the next best approximation after 22 over 7? Any general guesses? Well, 13 is a good guess, but unfortunately, math is not as reasonable as that guess. The right answer is actually 57 for some reason. But how is that possible? Why? It's 179 over 57 to be precise. But then you might expect, well, there was a continuous stream of improvement from 4 to 5, from 5 to 6, from 6 to 7. So surely, if we go to 58, that's going to be improvement over 57, right? But no. The next improvement is actually at 64. And the improvement after that is at 71. And the improvement after that is at 78. Now, hopefully you guys are noticing a small pattern in how the denominators are shaping up. So the question is, where is this pattern arising? And where does it end? Well, it ends all the way at the famous 355 over 113. Now, 113 is relatively large, but then you might wonder, oh, hi. When is the next best approximation after that? Well, it's not 113. It's not in the 100s. It's not in the thousands. In fact, it's not even in the 10,000s. It's 19,102. Well, that's the denominator. I don't exactly remember what the numerator was, but it was big. So what's happening? What's causing these erratic jumps from this approximation to that approximation? Of course, that's why you don't hear about anything past 355 over 113. The next best approximations are just too big. So what's causing the erratic jumps? And how do we apply this to numbers that are not pi? Well, that's when we introduce continued fractions. So what is a continued fraction? Well, of course, just like writing a number as a power series or with its regular old decimal representation, so just like you can write pi as 3.14159, but just like that, you can write it as a continued fraction. The continued fraction takes the form a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus 1 over a4 plus etc. This is probably the mathematical tool that you'll see today that has the most applications. And the continued fraction is very useful for a number of things, but it's also useful in the world of pure number theory. How? Well, first, let's find the continued fraction of pi. So how do we find these coefficients? What do they look like for pi in specific? Well, first of all, since this is, of course, going to be less than 1, since these are all integers, this is going to have to be the integer part of whatever number we're taking the continued fraction of. So pi's integer part is just 3. So that's what a0 is going to be. So the continued fraction is 3 plus 1 over a1 plus 1 over a2 plus so on. So then, what's the next coefficient? What's a1? Well, as you'll notice, what's over here has an integer part and a non-integer part. And so since this is going to be less than 1, a1 has to be the integer part of this entire denominator. So what we have to do is solve for this denominator and then take the integer part of the result. So we get x is equal to 1 over pi minus 3, and so the next coefficient is just the floor of this. And it turns out that is 7, the integer part, remember. So then, the next coefficient is just what happens when you repeat this process. You now know this is 3 plus 1 over 7 plus 1 over x. And you set this equal to pi. Now you need to find the integer part of x. And so you can continue this process over and over. It's very boring to do by hand, so people have just gotten computers to calculate continued fractions nowadays. And what happens is that pi's continued fraction looks a little bit like this. 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292. And it keeps going, because of course if it stopped, pi would be rational, since you can reduce any finite continued fraction to a rational number. So how does this relate to those approximations we saw earlier? Well, we started with just 3 over 1 is our first approximation. That's what happens when you just take this 3 in isolation. Then we started with 22 over 7 as our next test. That's what happens when 133 over 106. Nobody knows about this because there's a little optimization that happens right after that's so much better. Because this denominator is so small, it's just 1, it barely changes the denominator of the finished product when you reduce everything, but because it's another step down the continued fraction stairs, it has so much better accuracy than 333 over 106 that people forgot about this thing because it's just so bad compared to 355 over 113. And 355 over 113 is what happens when you take all of these. So you can keep going down the line, but the reason that the next convergent is something like 33,000, it's super large, is because of this 292 that pops up randomly. If you incorporate that into the whole thing, then of course the next convergent you're going to get will have an absurdly large denominator. And things with large denominators are impractical to use. At that point, just use the truncation method that we mentioned at the very start. So that's the story behind why those convergents are so good. In fact, continued fractions are the way to get the most efficient rational convergence to an irrational number. So now, we've explored exactly how to get the most efficient convergence. But another funny thing about math is that you want to explore, everything you can. And so some people started saying, well, okay, approximating things is boring. Now we have computer technology that can basically work with these truncated numbers already. 3.14159265 35897, and so many more. is a piece of cake for any computer to handle nowadays. Humans need 22/7, but computers don't care. And so mathematicians got bored. And they started saying, well, what happens if we actually just measure the rate at which these convergents continue to the number they're approximating instead? And it turns out, it seems stupid at first, but it can actually tell you so much about what the number is, including if it's transcendental. But how? Well, now this is going to be a little bit more involved in terms of mathematics than what we just did. So how do we do this? Well, the first thing I want to tell you is that this is not the land of common sense. There's rational numbers and then there's irrational numbers. Which one do you predict a rational approximation converges to faster? So, which do rational approximations converge to a rational number faster or an irrational number faster? What do you guys think? It converges to rational numbers? Now, see, that's the common sense approach. Unfortunately, pure math doesn't reward having common sense. Irrational numbers are faster, which makes no sense. It's baffling, but you can prove it with mathematics. Let's say when we measure the rate of a rational approximation converging to an irrational number or a rational number, here's the problem. As we showcased earlier, just because the denominator increases doesn't necessarily mean the approximation is better. Of course, the trend over time is that as the denominator increases, the approximation gets better. In fact, that has to happen, because if the denominator is 10, it's necessarily worse than if the denominator is 100, and that's necessarily worse than if the denominator is 1,000, and so on, for obvious reasons. You can include more of the digits with each bigger denominator. So, this is true for infinitely many q. But if you increase the power of this thing any higher than 1, it becomes false. But plus epsilon is false for or only gets satisfied finitely many times. However, for irrational numbers, you can show that this discrepancy decreases at a rate less than 1 over the denominator squared, which, as you can see, 1 over the denominator squared is, of course, a faster shrinking rate than 1 over the denominator. So, this is not to scale, of course. I'm pretty sure they actually cross some, so it's more like this. So, as you can see, in the long run, 1 over q squared is a lot smaller than 1 over q, which means approximations to irrational numbers are a lot better. Now, of course, I'm not just going to write you can show. That means nothing if you don't actually get to the proof. So how do we prove these? Well, let's start with irrational numbers. If we just write alpha as a over b, then we write a over b minus p over q. Now that can just be made into a common denominator. And here's the kick. AQ minus BP, this thing on the top, well, it's the difference of integers, which means, well, it's only going to be 0 if A over B is equal to P over Q. Which, sure, that happens infinitely many times. But here's the thing. The occurrence that A over B is not equal to P over Q also occurs infinitely many times. And so, if A over B is not equal to P over Q, remember the absolute value signs, this is at least 1. Which means that this, of course, is greater than or equal to 1 over BQ. And so, that means, well, 1 over BQ itself is a fine. We can say that if it satisfies 1 over BQ for infinitely many, so if you can say this is satisfied for infinitely many Q, you can also say this is satisfied. But, I mean, the problem is we've now shown that it's greater than or equal to. So, at minimum, it's worse than this. And of course, if it's worse than this, 1 over BQ at some point will be greater than 1 over Q to 1 plus any power. So this will eventually outgrow anything of this form. Which means if we can't show that the rational approximation satisfies something like this, of course we can only do less than 1 over Q. We can't increase the power at all. So you can show this for rational numbers. So how do you show this for irrational numbers? How is it any better? Well, here's the trick. Let's say you take some irrational number alpha and multiply it by an integer k. Then you can split it into the integer part and the decimal part. Notice this is indexed by k. Now, this only works for irrational numbers because, as you'll notice, for irrational numbers, no matter what integer you put here, the decimal part will always be non-zero. Of course, that's not true for rational numbers. So the decimal part will always be between 0 and 1. Now, here's what happens. You take the open interval 0 to 1 and partition it into, let's pick a number n. We'll call it big N. We partition it into n sections. So right now, n is 7. No, it's 2. Each of these has length 1 over n. Now, I'm going to take, so you know how this is dk right here? So that means that alpha is I1 plus D1. 2 alpha is split into integer part number 2 plus decimal part number 2. N alpha is equal to integer part number n plus decimal part number n. So just to make that clear. Now what we're going to do is take every decimal part from 1 to n plus 1. So that's, of course, n plus 1 numbers. Now, you guys, of course, know the pigeonhole principle. If you have n holes and n plus 1 pigeons to put into the holes, you will eventually end up with a hole that includes at least 2 pigeons. So, what that means is that when you have these guys, n plus 1 numbers, that are all bounded between 0 and 1, that are being shoved into n intervals, eventually you are forced to find 2 of them that are in the same interval. And so, if 2 of these decimal parts share the same 1 over n length interval, that implies that their distance, of course, is less than 1 over n. Less than root. So now what we can say is that plus 1 such that the difference between the decimal parts is less than or equal to 1 over n in this Pigeonhole principle. And so, what do we say now? Well, if we rearrange this just a little bit, we get k alpha minus ik. So this just becomes a alpha minus ia minus b alpha plus ib is less than or equal to 1 over n. Now, everything left comes all at once. We refactor this. And divide both sides by a minus b. Remember, we said that a and b were between 1 and n minus 1. That means a minus b cannot possibly be greater than n. It has to be less than or equal to n. And so, that means this is less than or equal to 1 over a minus b squared. So, what does that mean? Well, now, all we have to do is rename ia minus ib to p. Remember, integer part minus integer part. This is an integer. A minus b, integer minus integer, to q. And now we get alpha minus p over q is less than or equal to 1 over q squared. It's miraculous, and yet it works. It doesn't seem to make sense, but it does. So now, people noticed that you could show this for irrational numbers with the power equal to 2, and you could show this for rational numbers with the power equal to 1. So now they define something we call the irrationality measure. Me personally, I think that's a terrible name because you can't measure irrationality. It's either you are irrational or you're not. But the name stuck. So irrationality measure is just the highest power n such that alpha minus p over q is less than 1 over q to the n for infinitely many q. And so now, that implies through this, every single rational number has an irrationality measure of 1. Every single irrational number has an irrationality measure greater than or equal to 2. Now, what it actually is, well, now it's time to get into transcendentality. So, one day in 1844, a number theorist named Joseph Louville was wondering, well, okay, we have the irrationality measure of 1, 2. We can have anything we want. But can I find a number that somehow has infinite irrationality measure, whose growth for infinitely many q will always be less than 1 over q to the n for any n? And eventually he came up with the first transcendental number, what he calls Louville's constant. It's the sum from n equals 1 to infinity of 10 to the minus n factorial. What that means is that digit 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc. will have a 1. Everything else will have a 0. Which means in reality it looks something like this. Louville's constant. 0.1100001 on 0.0000001. So this should be 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, and so on and so forth. And so, how is this number irrational? Well, it turns out the best method of approximating this thing is just truncation. There's nothing complicated about this number structure. So what I'm going to do is write down all the possible approximations to this number. Approximation number 1 is just going to be 1 over 10, or 1. Now, the discrepancy here is going to be, well, I don't feel like writing it, but it's going to be 0.01, and all of the digits after the 0.01 were so insignificant compared to 10 to the minus 2 that we can basically ignore them. So, B1 is on the order of 10 to the minus 2. B2 is going to be 11 over 100, or 11 over 10 to the 2. So that's just going to be 0.11. And so D2 is going to be on the order of 10 to the minus 6, because the discrepancy is just going to be 0.000001. Everything after that is so insignificant that it doesn't matter. A3 is going to be, well, 110,001 over 10 to the 6. So, I think it's pretty predictable what it will look like at this point. And so, E3 is now going to be, well, we've covered everything up to this point. The next error will be over here, on the order of 10 to the minus 24, and so on and so forth. So, if we write an is equal to Pn over Qn, then the nth denominator, Qn, well, it looks to be 10 to the n factorial. See, A1 10 to the 1 factorial, A2 10 to the 2 factorial, A3 10 to the 3 factorial, and so on and so forth. And the corresponding discrepancy is 10 to the minus n plus 1 factorial, or 10 to the minus n factorial to the n plus 1, or 1 over Qn to the n plus 1. Now this is pretty genius. Why? Because anything with finite irrationality measure is competing against 1 over Qn to the k, where k is not dependent on n, which means that 1 over Qn to the n plus 1, where the power is dependent on n, will always be less than 1 over Qn to the k as soon as n plus 1 is greater than k. Which means at some point, this approximation is so good that it will be better than every single approximation of finite irrationality measure. And so he failed the first number with infinite irrationality measure. But how does that correspond to being transcendental exactly? Well, it's time to close off with probably the most involved proof today. Now, we're going to show that infinite irrationality measure does not just imply transcendentality, but it's pretty much one of the only ways to show transcendentality. Now, recall transcendental means non-algebraic, and algebraic means it's the root of a polynomial with integer coefficients. So what we're actually going to do is we're not going to prove this. We're instead going to prove that anything algebraic has finite irrationality measure. Now, this is a pretty ingenious proof technique. This is what we call Hoover's theorem. So what we're going to do is take an algebraic number alpha. And it's going to be the root of some minimal polynomial f. So of course that means f of alpha is equal to 0. And we can write f, since f is a polynomial, as some sum from I equals 1 to n, not 1, 0, from I equals 0 to n, if it's a degree n polynomial, of ai, the ith coefficient, times x to the I. So, since it's the minimal polynomial, we also know that prime of alpha is not equal to 0. That's going to be important later. Now, I'm going to draw this really quickly. I just remembered that I have another colored marker, so probably going to use that for visibility. So let's draw the minimal polynomial here. This right here is going to be alpha. And what we know here is that since f prime of alpha is not equal to 0, why can't I put the cap on the back? Oh, it's just not with those markers. Whatever. So we know that since f prime of a is not alpha is not equal to 0, since this root doesn't have multiplicity, in some epsilon radius, so we can pick some epsilon such that alpha minus epsilon to alpha plus epsilon is totally free of zeros. There exists zero such that if n is in alpha minus epsilon, alpha plus epsilon without alpha, n is not equal. So we now have this. Now what I'm going to do is draw f prime of alpha, which is going to look f prime of x, which is going to look I have that mixed up. So it goes down to 0 here, and then actually it becomes negative, and then just keeps decreasing. Which means that around the point of alpha, it's right here, just as we expect. So now, what I'm going to do here is take alpha minus epsilon to alpha plus epsilon, and over this limit, we know since this is a polynomial, it's going to be totally bounded. And what that means is that we can bound f prime of alpha between minus, how can I say this? Since we know that f prime of alpha is not equal to 0 over this whole interval, and we also know that f of alpha is continuous because I'm not keeping f of x is continuous because it's a polynomial. That means we can use the intermediate, the intermediate value theorem. So there will always be a bound on the values that the function can reach inside this circle because of the intermediate value theorem. And so, since the function and its derivative are bounded, I'm going to say that within this circle, f prime can be limited between minus m and n for some number n. Now, what I'm going to do is take some rational approximation. You can always find a rational approximation at any level of accuracy. So let's say we find a rational approximation right over here in the middle of the epsilon circle. Now, what I'm going to do is use the mean value. The mean value theorem is going to tell us that at some point in the middle of alpha and p over q, let's call it c, this derivative is just going to be equal to f of alpha minus f of p over q divided by alpha minus p over q Of course, this goes to 0 by our initial assumption, and I can rearrange this really quickly by first putting absolute value sums on everything. Then second, just switching cases with this. My writing is. And now, here's the ingenious trick. Since we know this about f, that means we can say f of p over q for some rational p over q is going to be ai p to the I q to the minus I. So now, if I plug that in here, I get the sum from, the absolute value of the sum from I equals 0 to n of a I p to the I q to the minus I divided by f prime of c over here. And now, I'm just going to write here q to the n, and over here q to the n as well. And this is going to give us I equals 0 to n, ai p to the I q to the n minus I over f prime of c, which is just a constant, which we know is bounded from the intermediate value theorem. So I'm going to call that constant, I don't know, v, and then q to the n. But of course, q to the n minus I, because this sum runs from I equals 0 to n, this has to be an integer, since this power will always be non-negative. And of course, that is an integer. This is an integer, because it's an integer raised to a power, integer power. And this is an integer by the assumption of the problem that alpha is algebraic, and it's a root of f. So this is an integer, this is an integer, and that is an integer, which means that their sum is an integer. So, I mean, it's going to be a really big integer for big values of n, but it's still going to be an integer. So at the end of the day, like the trick we use for differential equations, we can just write this as some constant divided by q to the n, which means that you've officially said that alpha minus p over q can be written as 1 over q as less than 1 over q to the n or something, but you can't go beyond that. This is c over q to the n, and so you've already shown that it's equal to c over q to the n, which means that it will be greater at some point than 1 over q to the n plus any number. And that means that for any algebraic number, as we've just shown, we're going to have some finite irrationality measure corresponding to the degree of the polynomial which we're root of. Like the square root of 2 can only have a maximum irrationality measure of 2, and it also has a minimum irrationality measure of 2. So, you know, we already know its irrationality measure off the bat. The cubic root of 2 has a maximum irrationality measure of 3, and so on. In fact, we actually know from a theorem in, I believe, the 1960s, called the Thue-Siegel-Roth theorem, that every algebraic number has measure 2. So now, we've shown that an algebraic number must have finite irrationality measure. And this has infinite irrationality measure, which means it can't be algebraic. But we thought that everything was algebraic back in 1944. We could always find a polynomial with integer coefficients that had some number as its root. But of course, this was the first number to break that mold, and thus this, instead of pi or e, was the first known transcendental number. So, that's it. I hope you all enjoyed this journey through pure math, and there are a few parts in here that could also be applied to physics, but I think this is mostly as pure as mathematics can get. Some of this has almost no application outside of mathematics. You know, continued fractions have lots of applications outside mathematics. But irrationality measure, it's really not usually useful to know if a number is irrational or not. If it's questioned that a number is irrational or not, usually that means if it's rational, it's going to have a huge denominator. And so there's not much practical difference for physicists. But I think no matter if you find that it has not much application to the real world, it's still sort of a form of art, actually. So I believe pure math is really, really beautiful, especially this part. So I hope that you saw that beauty today, even if you didn't follow the whole thing. Thank you everybody for hosting me and for listening to this entire lecture, and I hope you have a wonderful rest of your day.
Like this in complex numbers.
Yes, this is all about order, right? And there's no order on complex numbers. You can't say one complex number is less than the root of the number. So I think this might be a good idea. This could have been a good idea, but for most of the time, we have to deal with the real part of complex part of the irrational of the complex number. And of course, that was just reduced to the root. And so, I mean, it's exciting, but it also probably won't work with the black order.
So you talked about irrationality method, right? So for rational number, that there is one. And for algebraic number, you told that there is finite. And if the polynomial degree is n, then that is bounded to n, right? So what about t? Means what can you say about rational integer of t or pi? Can you explain how?
Actually, yes, that's been covered by a few papers. The irrationality method of E and pi, we did say that infinite irrationality method implies transcendental numbers, but that doesn't imply the converse. Some transcendental numbers, including E and pi, are known to have finite irrationality measures. In fact, there's been work on finding higher bounds for pi's irrationality measure. And right now we know it's less than 7.35. But we can't do anything further than that, because we don't know any technique so far for finding a lower bound for irrationality measure that's better than Q. So
What about e? Like,
E, I think the irrationality measure is less than 3.1. But I can't remember. So irrationality measure, as I said before, is a very misleading term. There were, transcendental numbers which have a low irrationality measure. And so, irrationality measure doesn't measure anything about irrationality. It just measures approximation accuracy. But yeah, I think that also studying the irrationality measure of transcendental numbers like E and pi is very interesting. And I hope there will be a breakthrough soon on finding lower bounds for these numbers.
okay, do you have any example of number or some classes of numbers? How do you that measure is infinite and not finite?
Yeah, we talked about the root of a number, but most of the time, when you have infinite irrationality measure, you have to specifically construct these numbers to get infinite irrationality measure. I can't think of a number that has relevance in another field that happens to have infinite irrationality measure, because they have to be constructed in a very specific way, like the root number that we saw before.
About that continued fraction. So it's keep on approximating very good. Where will I see that in a circle? Where will I see that in a circle?
Okay. I think. Okay. Yeah, I think. How would I say this? You can't really outright see it in a circle, but this continued fraction method is related in more than a couple of ways to the method of exhaustion that was used to calculate digits of pi in the old days, where people would take polygons with lots of sides, enclose one of them outside the circle and another one inside the circle in order to bound the value of pi. And these polygons, more often than not, have perimeter values related to these continued fraction conversions. But the circle directly, I don't think exactly relates to these conversions. No. Anything else?
Anybody else have a question?
Okay.
Thank you.